Everyone's here. So welcome. Our first speaker is Barbara Margolius. And she's going to tell us about time-varying QBDs.
Thank you very much. And thank you to the organizers. I really appreciate all the work that you guys have done. And as Federico said, I'm talking about spectral analysis of level-independent QBDs with time-varying periodic transition rates. So periodic phenomena are basically everywhere. So I've got kind of a sketch up here of seasons of the year, any process affected by that, or time of day. A lot of natural phenomena are periodic. Here's a picture of traffic at the border on Saturday. Airline traffic, call centers, all those things are periodic. So what are we doing in this talk? I'm going to provide an eigenfunction expansion for the asymptotic periodic solution to a variety of ergodic Qs with time-varying rates. So what's that mean? So the graph here is for a single server Q with time-varying rates given here and here, with lambda of t being the standard arrival rate, mu of t is the departure rate. And there are two sets of colored lines. The dashed ones are the periodic solution, and the solid ones are the asymptotic periodic. And as you can see in the plot, over time, the transient solution tends toward a periodic solution. And so what this talk is about is a method to solve directly for the periodic solution. So the periodic solution, asymptotic periodic solution, is analogous to the steady state solution for Qs with constant rates. So my goal for processes with a discrete state space is to find a probability generating function that looks like this. And so this is that phi is a periodic function with period 1, because I'm going to assume throughout that my period is of length 1. One can always rescale. And then it's got these chi-L, which are singularities of the generating function that I can use to find the probability of a particular number in the Q. For continuous processes like the fluid Q that we'll look at briefly at the end of the talk, this function will look like this. So this is the probability that the fluid level is less than or equal to x, and I can give it in terms of eigenfunctions phi that are periodic with period 1, and exponential things weighted by the singularities. So the method is a 6-step method. First, we take the system of differential equations that's particular to our model. We define either a generating function or a Laplace-Stieltjes transform. We find a generating function, we find a differential equation for that generating function or for that Laplace-Stieltjes transform. We solve it either initially for the transient solution and then for the periodic. And then we find the eigenfunctions in terms of those singularities and use that information to get the boundary values. So this is a lot of information pretty quickly, but I'm going to use a Department of Redundancy department approach and go through each of those 6 steps for each of several examples. I've got 6 examples listed, but I'm going to spare you all 6 and just do, we'll see how many we do. Backwards is not good. Okay, so we're going to look at a single server queue. We're going to skip the multi-server. We're going to look at a multi-server queue with catastrophes. I am aware this is a Matrix-Analytic methods conference, so we're going to look at level-independent QBD and what would be a level-independent QBD, but with catastrophes and repair, and then finally a cyclic stochastic fluid model. So I've got some mid-journey imagined Qs. This is what it might look like if Vermeer had painted it, and I did make an effort to use artists who had been dead for at least 70 years so that hopefully I'm not violating any copyright. Anyway, this is the x of t is the Q length at time t, lambda of t is the arrival rate, mu the departure rate, p sub n is the probability that there are n in the Q at time t. So we have the standard stochastic flow diagram here for a single server queue, which leads to this system of differential equations. Going to take the nth equation and multiply by z to the end and add them all up. And sorry, let me go back here. So there's a lot of equations in this talk. Just ignore them. Pay attention to my blue letters. So this is the first step of my process. This is a differential equation. We start with the differential equation system for the model. Then we define a generating function, so not gluten-free, but generating function, and find the differential equation that corresponds to that generating function. And notice here that I've got an unknown function on the left, the unknown function on the right times some factor plus some other term. So first or second week of your differential equations class, you can solve it from the method of integrating factors. And we get this transient solution. And if I let S up here, this is really testing my coordination. If I let S equal t minus 1, so I'm back 1 period, we're assuming that the process has an asymptotic periodic solution, so this equals this. And so I can bring this term over to the left-hand side, factor out 1 minus that exponential, and I can get the periodic solution. There will be values of this factor such that it's equal to 0, and we're dividing by that. And so those values of z such that that thing is equal to 0 are going to give us singularities, and we can use those in order to express the solution in terms of eigenfunctions. So side note, this exponential goes by several different names. It's the fundamental solution, the homogeneous solution, Green's function, evolution operator, and a random walk generating function. And which of those is most appropriate depends on your perspective. I'm generally going to call it the random walk generating function. So the coefficients on z for this guy are going to give you the probability of n more steps to the right than to the left for a random walk with those transition rates. Okay. So this is the general form for the eigenfunction solution. There's my eigenfunction, that phi. And then I got this guy. The roots of the denominator are going to be the values of z such that the exponent on the exponential is equal to 2 pi I L, where L is some integer. And so that's just a quadratic. And so we're going to get two solutions, plus or minus here. We're only interested in the one with the plus because the ones with the minus would be inside the unit circle, and so their reciprocal would be outside of the unit circle. And you would not get an ergodic Q, it would blow up. And the way that that issue is resolved is that for the zeros in here, the numerator is also 0. So let me just take a moment and refresh your memory of complex analysis. This top graph is a plot of z, and this is a plot of 1 over z. We're looking at the generating function is a complex function. It takes a complex argument and returns a complex value. So that's 4 dimensions. So these are plots in the complex plane, and it's showing the value of the function in polar coordinates. The color refers to the angle with the origin, and the quilting sort of stuff here is the distance from the origin. We're only intending qualitative value here, not that you can read off numbers off of these graphs. So you notice that all the colors come together in the middle of each of these graphs. That's because the angle doesn't matter at a pole or at a 0. Notice also that the order of the colors is reversed here versus here. So when I have a 0, the colors are going to go in Roy-G Biv order as the angle increases, and in the reverse order if it's a pole. This is a plot of the denominator, so the poles of the generating function will be zeros of the denominator. And so you can see them here kind of tending almost to a vertical line. These guys are just going to go away because the numerator will be 0 there. So I have a movie. I have to figure out how to get the movie to start. So the generating function is a function of time. And yeah, I lost my movie. I'm just going to try and make it loop here. So see the white dots here? These are where the singularities are. Notice that as we loop through time, they're not moving. They don't depend on time. But the coefficients on the 1 over 1 minus z over chi, those do depend on time. And so that's what you're seeing changing. This graph on the left is the absolute value of the generating function. So you can see all the poles, they look like poles. And then this is a phase portrait. So let me just make that go away. I keep wanting to touch the screen. That's a bad idea. Okay. So continuing on, this is the eigenfunction expression. We're just using complex residue theory. So near one of these singularities, the function is going to act like the residue divided by z minus the root. And so if I factor out -1 over chi L, then I have it as something or other times 1 over 1 minus z over chi. And I can expand that as a geometric series directly. So I don't know if this is going to show up on the thing, but I know it's elementary, but sometimes it's just a good idea to see some elementary idea explicitly written. So, right? So from the functions that I've got, you can just immediately find the coefficients on z to the n, and then you can find the distribution of the number in the Q. So this is how we find the constant CL that appear here. And then using the information that we got above, we can get this unknown boundary probability. I'm going to skip that. And so here's our basic setup in terms of the eigenfunction and this thing that we can expand in a geometric series. And so for general n, there's the solution for a single server Q. And in particular, when n equals 0, it's just the probability that there's 0 in the Q is just the sum of the eigenfunctions. And so we can use our generating function for the whole series to find P0 in terms of itself. All right, so there's a Q as John Singer Sargent might have painted it. And I'm just going to go skip this part. Go here. So you recognize this notation. In addition, I've got failures occurring at rate gamma, repair occurring at rate eta, and multiple servers, and there is some probability of being in a repair state, but otherwise the notation is the same as the example we already saw. There's a stochastic flow diagram for this, and we have our system of differential equations. So pay attention to the blue, right? There's differential equations is the first step of my 6 steps. We define the generating function, that's the second step. And from the differential equations and the generating function definition, we can get a generating function differential equation. And now we've got something that we could have solved in the second week or first week of our differential equations class undergrad, and we get the transient solution. And if we let S here and there equal t minus 1, then this generating function equals that one. And so we can get the periodic solution. We're interested in the singularities of this generating function. So we've got the same basic structure as before. There's the eigenfunction form of the solution. This denominator, the denominator on the previous page, I guess, is going to be equal to 0 whenever this function is equal to 0, which is going to be when that exponent is equal to 2 pi IL for L an integer. And so this is just quadratic. We've got this extra term here, but it's still just quadratic. These bars just mean the average value of the function over an interval, over a single period. And so we get this solution. We don't care about the one where this is negative because that's inside the unit circle. And so this looks very much like the one we saw before. The eigenfunction is just given by the solution to the differential equation we evaluated at the singularity. And the constant CL, we can use this residue formula to find it. And the boundary values, we can use the initial part of that system of differential equations we started with, and the fact that probabilities have to sum to 1 to get those guys. I'm going to skip that. And this is a cue if Tiffany had done it in stained glass. So quasi-birth-death process. I use the convention that the subscript on the A matrices tells whether we're going up a level, down a level, or staying in the same level. This is a process with a bivariate state space, as we probably all know here, but I'm going to say it anyway. So x of t is the level, j of t is the phase at time t. We're assuming that we've got little j number of phases, and so these are square matrices that are j by j. This is a j component vector that gives the nth component gives you the probability of being in phase m at time t and in level n. So with that notation, and here's just a snippet of a stochastic flow diagram for one particular example of a level independent QBD. 1, differential equations. 2, generating function. 3, generating function differential equation. Method of integrating factors, so we solve it, get the transient solution. Let S equal t minus 1 here and here and here. And I'm going to skip this, go back to this next slide here. Then we get the periodic solution as before. So let me go back to the slide I skipped. Phi acts like a matrix exponential. Its derivative with respect to time is itself times az of t, which is this. Its derivative with respect to u is minus az of u times itself. If u equals t, it's the identity matrix. It is a fundamental solution, a homogeneous solution, a Green's function, a random walk generating function. You can look at it all those different ways. This is actually a trivial generating function here for going up a level or down a level. And we already saw this. And here's the eigenfunction form of the solution. The chi-L are just the solutions of this determinant equation. In general, you're not going to have an explicit formula for them. So you've got to get it numerically. Sometimes there's an explicit formula. It depends on if it's a highly structured solution of a particular type or not. We get the CL in the same way that we did before. There's the eigenfunction, which is just the numerator that we saw before with the singularity plugged in. And again, we can get these boundary values using the ordered differential equation system that we started with and the fact that the probabilities must sum to 1. Skip that slide. So for a QBD, the generating function is a vector. So this is just a really trivial one with j equal to 2 for 2 possible phases. So notice I added again the white dots to show where the singularities are. Notice that most of the singularities inside the unit circle have been wiped out. There's a little bit of numerical issues, and some of those are probably actually zeros. They're the same singularities here as here, and they're not moving with time. They never move with time, and that's actually something really easy to prove with Sylvester's theorem, which we won't do. Okay. So here's a cue as it might look in Dante's Inferno. So we can do basically the same approach for a quasi-birth-death process except that it's also got a failure rate and a repair rate and a state when it's in repair. And so it looks much like the previous example, but instead of just A0, we've got A0 minus gamma I. And so there's my system of differential equations, number one. Number two, define the generating function. Solve the differential equation. Well, find the differential equation for the generating function. Solve the differential equation for the transient solution. Set S equal to t minus 1 here and here. And get the periodic solution. So there it is. In the previous slide, I just skipped the definition of phi, but it's very similar to what we saw on the preceding slide. We then express it using our eigenfunction approach. And the eigenfunctions are just going to be this expression, but we plug in the singularities here and here, and into the adjoint of this I minus phi matrix in order to get the generating function. And we also need to find the constant C to multiply that by. So the chi-L are the roots of this determinant equation at the top of the screen. The eigenfunction is, as I said, we just plug in chi-L. And so we're going to get this expression here for the eigenfunction. And CL is just found by using this residue theorem. And again, near the singularity, it's going to act like this thing evaluated at chi-L divided by this. And this we just expand in a geometric series in order to easily pluck off the coefficients on z to the n. So there's CL. And we get the boundary values in the same way. Skip that slide. Here's a Q as Edward Hopper might have painted it. So last example, I'm going to look at a fluid Q. So now the state space is continuous. We have a background finite state continuous time Markov chain with little j states, and that is the state of that chain is given by j of t. And x of t here is the fluid level at time t, and that's continuous. C is the rate at which the fluid flows, and that is dependent on which of the states of the background process the process is in. Capital T of t is the generator for the background process. Little lambda here no longer has anything to do with arrival rates. It's just a parameter for the Laplace-Stillches transform. And what we're looking for is this PTX, which is a joint probability mass in the phase of the background process and probability distribution in the fluid level. So that's what we're going to compute. So number one, differential equation. That's right here. Instead of defining a generating function, now we define the Laplace-Stillches transform, so that's number two. Then we find the differential equation for that guy, that's number three. And notice that we have our derivative of our unknown function here on the left, our unknown function times some factor on the right, plus another term. So we use our first or second week of differential equations to find the transient solution, and that's given up here. And then we set S equal to t minus 1 and move this term over onto the left-hand side and factor out pt lambda. And we get this periodic solution. I don't have a slide defining W tilde, but it's totally analogous to the phi that we have in the discrete time case. So its derivative is itself times t minus lambda c, I believe. Okay, and here is the periodic solution. Here is the solution in eigenfunction form. The roots are going to be given by the zeros of this determinant. And then here's a phase plot of just the denominator, of the determinant of I minus W. So it's similar but different to what we were seeing in the discrete state space case. I've got some positive, some zeros with positive real part, but again, in the numerator of the Laplace-Stillges transform, those will be zeroed out. They're removable singularities. And these guys we're stuck with. Notice that they're tending toward a regular pattern. That's always going to happen. It's based on what the mean value is of the infinitesimal generator for the background process, but you can tell pretty easily what the asymptotic behavior of that's going to be. And in this example, it's tending toward it pretty quickly. And we're not going to go through that. Here's our eigenfunction. And the constant C is computed in this way. And we get the boundary values using the information we got above and making sure it satisfies the differential equation we started with. And then here's some comparison data of simulation. It's like a million event simulation average against the analytic solution from this methodology. So, and this, I should have mentioned earlier, this work on the fluid model is joint work with Margolius O'Reilly. So you can see that it's basically the same. And so to sum up, we start with a system of differential equations relevant to the model that we're studying. We define either a generating function or a Laplace-Stillges transform. We find the generating function differential equation or the Laplace-Stillges transform differential equation. Solve it for first the transient case and then the periodic. We find the eigenfunctions and then use the information above to get the boundary values. And thank you for your attention.
Barbara?
I have one more